And being more crazy does not necessarily mean more wrong. I have chosen 6 examples, the traditional half dozen, largely in order to justify using the quotation from Alice. I have my own views on their relative merits, which I hope I shall not reveal, leaving you to make your own choice, or, indeed, to stick your fingers in your ears while going, la la la, I can't hear you. Before offering those interpretations, though, I ought to make it clear just what it is we are trying to interpret. Science often proceeds in fits and starts. In this case, though, it seems appropriate to begin with another nod to Charles Lutwidge Dodgson, with 2 fits. John Gribbin, June 2018. 1. Fit the first. The central mystery. The weirdness of the quantum world is encapsulated in what is formally known as the double-slit experiment. Richard Feynman, who was awarded the Nobel Prize for his contributions to quantum physics, preferred to call it the experiment with 2 holes, and said that it is a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery, the basic peculiarities of all quantum mechanics. This may come as a surprise to anyone who only remembers the experiment from school physics, where it is used to prove that light is a form of wave. The school version of the experiment involves a darkened room in which light is shone onto a simple screen, a sheet of card or paper, in which there are 2 pinholes, or in some versions 2 narrow parallel slits. Beyond this screen there is a second screen without any holes. Light from the 2 holes in the first screen travels across to the second screen, where it makes a pattern of light and shade. The way light spreads out from the 2 holes is called diffraction, and the pattern is called an interference pattern, because it is the result of 2 beams of light, one from each of the 2 holes, spreading out and interfering with each other. And it exactly matches the pattern you would expect if light is traveling as a form of wave. In some places the waves add together and make a bright patch on the second screen. In other places the peak of one wave coincides with the trough of the other wave, so they cancel each other out to leave a dark patch. You can see exactly the same kind of interference pattern in the ripples produced on a still pond, if you drop 2 pebbles into it at the same time. One of the distinctive features of this kind of interference is that the brightest patch of light on the second screen is not directly behind either of the 2 holes, but exactly halfway between those points, just where, if light was actually a stream of particles, you would expect the second screen to be completely dark. If light was made of a stream of particles, you would expect to see a bright patch behind each hole, and darkness in between those patches of light. So far so good. This proves that light travels as a wave, as Thomas Young realized at the beginning of the 19th century. Unfortunately, at the beginning of the 20th century, another kind of experiment showed light behaving as a stream of particles. These experiments involved electrons being knocked out of a metal surface by a beam of light, the photoelectric effect. When the energy of the ejected electrons was measured, it turned out that for any given color of light, the energy of each electron was always the same. For a bright light, there are more electrons ejected, but they still all have the same energy as each other, and this is the same as the energy of each of the smaller number of electrons ejected when the light is dimmed. It was Albert Einstein who explained this in terms of particles of light, what we now call photons, or in his language, quanta of light. The amount of energy carried by a photon depends on the color of the light, but for any color, all photons have the same energy. As Einstein put it, the simplest conception is that a light quantum transfers its entire energy to a single electron. Turning up the light just provides more photons, light quanta, each with the same energy to give to the electrons. It was for this work, not his theories of relativity, that Einstein was awarded the Nobel Prize. After 100 years of thinking of light as a wave, physicists had to start thinking of it as a particle. But how could that explain the experiment with 2 holes? It got worse. After seeing the wave nature